this video, we're going to talk about the difference quotient, the type of the difference quotient that we're going to talk about right now in this video is going to look like this. I'm going to take a minute to explain what that is. If you are in a calculus course, you're not going to use the letter H, you're going to use the letter delta X instead. Symbol delta X, and that is the same thing. And I'm going to use this second form of it here so that I can say that my slope, which we call M, is equal to y2 minus y1 over x2 minus x1. And in calculus, we call this change a delta. And we use the Greek letter delta, which looks like a triangle, like that. You may have seen the letter delta before in some things like fraternity or sorority names. That's all it is a capital letter D in Greek. And we use it, as I said, in math and science to represent change in something. So the difference between a final value and an initial value. So if I were to draw a picture here of something that was linear, to make this easy, there's my function. It's going to be f of x. And I'm going to draw a picture here that this is going to be my delta y, which is going to be my y2 minus my y1. And this is my delta x on this side, which is my x2 minus my x1. And my slope here is my rise divided by my run here. So now let's go ahead and let's start putting some stuff in function notation here. So I'm going to call this point down here x f of x, since I called the function here f of x, that when I put in an x value, I get an f of x value. And I'm going to call this horizontal distance here delta x. But for the sake of writing things out and not having too many x's in pre-calculus, we're just going to call that horizontal distance there h. And that means that this point up here has an x coordinate of x plus h, and its y coordinate is whatever f of x plus h is. Now, if we were to find the slope of this line that connects these 2 points, x f of x and x plus h f of x plus h, we would have our y2 minus our y1 over our x2 minus our x1, and this x and that negative x would make a 0, and I'd have my formula for my difference quotient. So all it really is the slope formula, and we know the restriction there, h can't be 0 because I'm not allowed to divide by 0. Now, why do we care about this? It looks pretty silly if it's a line, but what I'm going to have most of the time is that f of x is not going to be linear. It's going to be something that's curved, and I'm going to have these 2 points are connected by something called a secant line. And I'm going to have a f of a, b f of v type thing for an average rate of change. But if these points are fairly close to one another, then I can just use the difference quotient idea here to approximate them. It's really the same thing, but if I call this point here x, f of x, if I call this point over here x plus h, f of x plus h, then I've got my difference quotient for my slope of my secant line. I could write that as a f of a and b f of b, and I could write it as f of b minus f of a over b minus a. We'll call that average rate of change later. Or I could use f of x plus h minus f of x divided by h, where h is not equal to 0. In this case, a is not equal to b because I don't want the denominator to be 0 in either case. So why we care about that, we'll get to when we talk about the tangent line problem in calculus, but for right now, this is pre-calculus, and we are doing this because it is a setup to get to something later in calculus. You're not going to really understand the totality of how this is going to help you until we get to something called a derivative later, but you're doing 90% of the work of a derivative problem here in pre-calculus by finding the difference quotient. So we've got 3 different types of problems that we've got techniques for finding the difference quotient. And we've got our first type is polynomials. And they're pretty straightforward. Our second one is going to be, rational. And our third one is going to be radical functions. And I've got examples for the first 2 here, and I'll come up with an example for the third one in a second. So let me clear this. So let's start off with f of x equal to 9x plus 4. This is a linear function, which is the most basic form of a polynomial. We already know that we're headed towards the slope. A slope generating function is what I showed you that we were going towards. So because this has a constant slope, we can just hypothesize here that the answer to this function, this difference quotient function, should be 9 because we know that that is the slope of this line. It's a constant 9. So let's see if we get that. So if we have f of x plus h minus f of x divided by h, that's going to be 9 times x plus h plus 4 minus the quantity 9x plus 4. And all that gets divided by h. And off to the side here, we know h can't be 0. So I'm going to take this left-hand side and I'm going to replace it with the abbreviation dq for difference quotient. That's going to be 9 times x plus 9 times h plus 4 minus 9x minus 4 divided by h. Again, h is not 0. What we're going to see is the stuff on the right-hand side from the minus f of x is going to 0 out with things over there for my f of x plus h. That's only leaving me with my h terms left. And because h is never equal to 0, this is never a 0 over 0 situation. It's really close to that, but it's the same non-zero number divided by itself. That's going to give me a 1. So my difference quotient, in this case, I'm allowed to do that division because I'm not getting 0 in the denominator. My difference quotient is 9, just like I expected it to be. Let's go ahead and clear this out. Let's look at another example here that is a polynomial of higher degree than 1. And I highly recommend using Pascal's triangle to help you expand these things if you get higher degree things than that. I have a video on Pascal's triangle that you can look for in other pre-calculus videos that I've made, but I'll just show it again here. Form Pascal's triangle by writing ones on the outside, and then anytime that you can add two numbers together, you do, and you put the number in the middle. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3. If I wanted the next row, it would be 1, and then 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and the 1 comes on the outside. This is useful for things in statistics that we call combinations, things in discrete math we call combinatorics. It's also very useful in the binomial theorem later in pre-calculus, which is part of what we're doing here. I'm just going to look at the f of x plus h part all by itself here in this one. And then I'll add in the other stuff in a second. So with that, I need to square x plus h. So this is, for the binomial theorem, these are my coefficients when it's a constant. This is for when it's linear. This is for when it's quadratic. So I want that pattern of 1, 2, 1. I'm going to have a 1x squared plus 2, and I'm going to take an x away and add an h in, plus 1 of, I'm going to take an x away and add an h in, like that, plus 8x plus 8h plus 5 is what my f of x plus h is. Now I'm going to subtract my original f of x from that, and I have a minus x squared and a minus 8x and a minus 5. So all of my terms without h's are going to become 0. So the f of x plus h minus f of x is going to leave me with a 2xh plus h squared plus 8h. I'm going to divide everything by h here. So let's just divide everything by h, and we get that the difference quotient on the left-hand side here is equal to 2x plus h plus 8, and we know that h can't be 0. It's okay that the difference quotient ends up with h's inside of it sometimes. And in linear functions, all those h's are expected to go away. But in nonlinear functions, those h's are expected to stick around and be part of your answer. Let's go ahead and let's look at this example of f of x equal to 1 over 6x. So my f of x plus h this time is going to be 1 over 6 times x plus h. When I subtract my f of x from that, I get my f of x plus h minus my f of x. is equal to, this is subtraction of fractions. And I want to make a common denominator here. So I'm going to multiply here by 6x over 6x. I'm going to multiply here by 6 times x plus h over 6 times x plus h. That's going to equal for me 6x minus 6 times x plus h over oops, I multiplied by 6's where I didn't need them here. I'm just going to multiply by x over x here, and I'm going to multiply by x plus h over x plus h because I've got 6 as a factor in both of them. So this is going to be x minus x plus h over 6x times x plus h. There we go. And then we're going to, again, this is only f of x plus h minus f of x. This is x minus h over 6x times x plus h. So f of x plus h minus f of x is equal to a negative h over 6x times x plus h. I am now going to divide by h. When I divide by h over here, that makes my difference quotient equal to a negative h over 6x times x plus h times the reciprocal of h. So those h's will cancel since they're not equal to 0. That leaves me with a negative 1 over 6x times x plus h not equal to 0. All right, I want to do one more example. Even though this video is a little bit longer, this is an important concept. So we're going to do one more thing here where I have a square root, like so. And I want to find the difference quotient of it because it has a different technique that you're probably not used to. So when I want to find f of x plus h, that's pretty straightforward. And then when I subtract f of x from it, and we're going to divide by h. And I know you don't see a problem, but there's a problem here that I need to rationalize my numerator. And that's not something that you've ever been told to do before. You might have been told in the past to rationalize your denominator, but you've probably never been told to rationalize your numerator. So we have to do that in this case, even though you don't know why. It will become apparent when you get to calculus class. And we're going to do that by multiplying by the conjugate, which means the same thing with the opposite sign here. Top and bottom, we're going to use the idea that if I multiply things that are the same but have opposite signs, like so, that it's a difference of 2 squares. We've been doing that factoring technique for a while. So my difference quotient is going to be, and so it's going to be the first part squared, gets rid of that square root. minus the second part squared gets rid of that square root, and there's nothing left in the middle. I'm gonna bring this up here. So my difference quotient here is going to be x plus h plus 2 minus x minus 2 times x plus h plus 2 square root x plus 2. And again, anything over here on the right hand side is going to cancel out. It's going to zero out with something in the f of x plus h. I'm going to be left with only my h terms. And these are going to cancel to leave me with a 1. And my difference quotient is going to look pretty funky to you. That's okay, because my goal was to cancel out that h. And the only way to do that was to rationalize my numerator. And remember, h is not equal to 0 there. So those are a few examples of the difference quotient. I did a linear problem, a quadratic problem, a rational problem, and then I did a radical problem. Hopefully that helps you prepare for the different types of problems that you're going to have in pre-calculus. And I have done many more videos on this topic too, so just go ahead and look in the pre-calculus and college algebra videos if you want to find more videos on just this with plenty more examples. There's also plenty of them in my preparing for calculus videos as well. All right, have a good day.